In this video, we're going to introduce arc length and curvature. So, back when we studied parametric equations, we talked about how to find the length of a parametric curve, assuming that the curve was drawn out once on the interval from a to b. We did the sum of the derivatives of each variable squared, and then took the square root of that, and integrated it from a to b. So that was our arc length formula back for parametric equations. We can define the length of a space curve in exactly the same way. Again, we want to make sure that the curve is traced out exactly once on the interval from a to b, but provided that your f prime, your g prime, and your h prime are all continuous functions, then we can calculate the arc length by doing the square root of the sum of the squares of the derivatives, and then integrating it. Notice this looks a lot like the distance formula, and that's exactly where this comes from. You are doing distance between consecutive points. If you approximate the curve with line segments, you're doing distance between consecutive points, adding all those distances and recognizing that you have a Riemann sum. So that's where the formula actually comes from. Well, we notice that the inside also looks like a magnitude. So if we think of the derivative being the vector valued function f prime, g prime, h prime, then we can rewrite the arc length formula in a more succinct form as the integral from a to b of the magnitude of r prime of t dt. So let's do a quick example. Let's suppose we have the vector valued function sine t, cosine t, log cosine t on the interval from 0 to pi over 3, and we want to find the length of that curve. First, we take the derivative of the vector valued function. Derivative of sine is cosine. Derivative of cosine is negative sine. Derivative of log of cosine will be 1 over cosine times a negative sine or negative tangent. On the interval from 0 to 3, those three component functions are continuous, so we can apply the arc length formula that we just mentioned on the previous slide. We'll do the integral from 0 to pi over 3 of the square root of the squares of each of the components of the derivative. So we get cosine squared plus sine squared plus tangent squared. Cosine squared plus sine squared is 1. 1 plus tangent squared is secant squared. Square root of secant squared will just be secant. So that integrand simplifies to just secant of t, which we're going to integrate from 0 to pi over 3. Antiderivative for secant is natural log of secant plus tangent. Plugging in our endpoints, we get natural log of 2 plus root 3. All right, we also need to talk about what's referred to as the arc length function, because where we're headed is to try to figure out some sort of a measure for how much a function, a space curve, bends. To do that, we need to be able to measure the space curve in terms of a unit arc length, if you will. To do that, we need to define what the arc length function is. Well, the arc length function is just that same integral. We're just going to replace the upper limit of integration with a variable and write that in terms of a function then. Again, we need to make sure that we have a continuous derivative for our vector valued function and that we only trace out the curve one time. So one thing that we do with this, and what I alluded to when we first started this slide, is that sometimes we'll want to reparameterize the curve with respect to the arc length, because we'll want to try to figure out how much the function bends in terms of the unit of how long you've gone on the unit in terms of how long you've gone on the function. So a unit distance on the function, not necessarily a unit distance in the x, the y, or the z direction. So in order to be able to parameterize the curve with respect to arc length allows us to figure out a unit length on a curve. So let's look at this example where we have the vector valued function 1, e to the t sine t, e to the t cosine t, and we're being asked to reparameterize this vector valued function with respect to the arc length starting at t equal to 0. So we would first differentiate the vector valued function. And we're using u's here for the derivatives rather than t's because we've got t up in the upper limit of integration. Each of these comes about using the product rule. So you should be able to verify that those really are the derivatives of your y and your z components. Derivative of your x component, of course, here is 0. We should be able to multiply this all out to get this large expression, but it really isn't that bad because we notice when we add e to the 2u sine squared u with e to the 2u cosine squared u, we just get e to the 2u. And we have 2 of those, so it should be a 2e to the 2u under the radical. And notice that the ones with the mixed sines and cosines cancel each other out. So simplifying that, we get root 2 e to the u du. Antiderivative of e to the u is just e to the u. And then so we'll get e to the, square root of 2 times e to the t minus 1. So we want to solve this for t so we can plug something in for the t to reparameterize in terms of s. So divide by the square root of 2 and then add 1 and then take natural log. That gets us the t in terms of s. And now we can plug that back into our original vector valued function. This gives us now a parameterization of that curve in terms of arc length. Now, it's not necessarily a pretty parameterization, but it is a parameterization of the function in terms of the arc length. So again, the process is to, going back to the previous slide, we found the arc length function for some arbitrary upper limit of integration. So we get a function s of t, s in terms of t, rearranged and get t in terms of s, so that we can plug that t value back into the original function to find a new function parameterized in terms of arc length in terms of s rather than t. So we mentioned that we need to be able to parameterize a curve in terms of arc length to look at curvature. We also need to have some sort of a way to measure exactly what's turning in order to measure curvature. And again, we want to standardize this, make it in terms of a unit length, if you will. So to do that, we're going to define what we refer to as the unit tangent vector, and that'll be equal to the derivative of the vector valued function divided by the magnitude of the derivative. So we're going to have a unit vector that points 1 unit in the direction of the r prime of t vector, or the tangent vector, if you will, at that point. So we can measure how much this unit vector changes with respect to arc length if we change the parameter over to arc length rather than just whatever t we're given. So this is the measure that we're going to refer to as curvature. So to find the curvature, as a messy way to find the curvature, that we won't actually do this to find the curvature generally speaking, but the definition is we want the rate of change of the unit tangent vector. How is the unit tangent vector changing with respect to the arc length in a length sense, in a magnitude sense? Okay, so we'll take the magnitude of the derivative of the unit tangent vector with respect to arc length. It would be helpful if we had a curvature formula in terms of t rather than s, so we wouldn't have to reparameterize the curve every single time in order to find its curvature. So let's do that. So if we have the arc length function as a function of t, we can use the chain rule to find the derivative of the unit tangent vector with respect to t. That's the product of these derivatives. This is just a chain rule. This is the same thing as t prime. It's just another notation. That's just another notation. The derivative of this should be a d, not an s. This should be ds dt. My apologies, that's a typo. This is the derivative of the integral of the magnitude. Remember, s is defined as the integral of the magnitude of the derivative. So when we differentiate the integral, we just get the magnitude of r prime of t. Take the magnitude of both sides. Well, this is just a constant. The magnitude of r prime of t is just a constant, so I can pull it outside the magnitude. This expression on the right factor here is we can recognize as the curvature. I don't know why I wrote typed the same line twice, but this is just the curvature. If we solve for curvature, kappa, we'll get the derivative of the tangent vector over the derivative of r. and doing the magnitude of each piece. So let's see if we can do an example here rather than me talking about it. Let's see if we can apply the formula. Here's the helix cosine t sine t t. This would be a helix that goes around the z-axis. It just keeps going around and rising above rising and falling around the x-axis. Take the derivative, we'll get this vector valued function. Take the magnitude of the derivative, we see a sine squared t and a cosine squared t will be 1, so the magnitude of the derivative will be root 2. The unit tangent vector is the derivative over the magnitude of the derivative, so we'll just get 1 over root 2 times the derivative function. The derivative of that is 1 over root 2 times negative cosine t, negative sine t 0. Finding the magnitude of that vector is 1 over root 2. So now we can find the curvature. It's the magnitude of the derivative of the tangent vector over the magnitude of the derivative of the vector valued function. So we'll get 1 over root 2 all over root 2, which gives us a half. That formula involved the derivative of the unit tangent vector. Again, that's a step that we'd rather not have to take if we don't want to. So we can develop a formula for the curvature in terms of just r of t and its derivatives. Here's our definition of the unit tangent vector. The next line is just clearing the fraction. Another name for the magnitude of the derivative function is the derivative of the arc length with respect to time. Differentiate both sides. We get r double prime of t is the derivative of the tangent vector times ds dt plus the tangent vector times the second derivative of the arc length with respect to t. Now let's take the cross product of r prime and r double prime. We can distribute the r prime of t to each term in the sum, and then rewrite what r prime of t is equal to. We have that over here. R prime of t is, oh, there's missing a cross product. There should be a cross right in here. This should be t of t ds dt cross t prime of t ds dt. And then a t of t ds dt cross t of t ds d, the second derivative as with respect to t here. Sorry about that. The ds dt and the second derivative s with respect to t, those are scalar functions. So remember, scalars we can just pull out in front of the cross product. Then we were left with, in the second term, we were left with t of t cross itself. With any vector cross itself is 0. So the second term here goes away. So all we're left with is t of t cross t prime of t times ds dt quantity squared. Now, remember that the magnitude of t is always 1 because it's the unit tangent vector. T of t and its derivative are orthogonal to one another. And from a formula for the cross product, we know that the magnitude of the cross product is the product of the magnitudes times the sine of the angle between them. Since these two vectors are orthogonal to each other, we can write this as sine of pi over 2. The angle is pi over 2. Sine of pi over 2 is 1. This is also 1. So we just get the magnitude of t prime of t. So, going back to this line, taking the magnitude of both sides, we would have the magnitude of the cross product of r prime and r double prime is equal to the magnitude of t prime times the square of ds dt. ds dt, again, we can rewrite as magnitude of r prime. So we get the magnitude of t prime of t is the product of the magnitude of the cross product of the first and second derivatives over the magnitude of the first derivative squared. Finally, dividing both sides by the magnitude of r prime gives us this formula with the magnitude of r prime cubed. And we recognize now that the left-hand side is the curvature. That was a long way to get there, but this is the curvature formula in terms of r prime and r double prime. So let's see if we can use that for an example. Let's say we have the vector valued function r of t is equal to t cubed 0 t squared. First, take the derivative. And take the second derivative. Take their cross product, and I'll let you verify the details that the cross product of those two vectors will be 6t squared j. That means the magnitude of the cross product is just the 6t squared, because we only have the one component from the vector. Magnitude of r prime is square root of 9t to the fourth plus 4t squared. So now we take the magnitude of the cross product and divide by, oh, this should be cubed. This should be not just the square root. It should be the square root of 9t to the fourth plus 4t squared cubed, or write it as 9t to the fourth plus 4t squared raised to the 3/2. Switching gears a little bit, let's talk about the normal and bivariate normal vectors. We know that the unit tangent vector and its derivative are orthogonal, but just because we have a unit tangent vector doesn't mean its derivative has a magnitude of 1. We can change it to a vector that has a magnitude of 1, though, by doing our standard divide by the magnitude, and we'll call that the unit normal vector. So here's its definition. The bivariate normal vector is the vector that's orthogonal to both t and n by taking its cross product of the two. So let's see if we can find these three for a specific example at a particular point. All right, so to find these, we'll have to first find the unit tangent vector, take its derivative, scale it to 1, take its derivative to find the unit normal, and then take a cross product. So here's the derivative of the vector valued function. You can check that. Here's how we would calculate the magnitude. That simplifies to 5, because your sine squared plus cosine squared equals 1. Since the magnitude is 5, we find the unit tangent vector by just dividing our derivative by 5. We can now find the derivative of the unit tangent vector. Take the magnitude of the unit tangent vector. We'll get 3/5 in that case. Which means our normal vector, our unit normal, will be 1 over the magnitude of the derivative. That's where the 5/3 is coming from, the reciprocal of this, times the 1/5 of the 0, negative 3 cosine t, negative 2 sine t. We should get, this is not a 2, this is supposed to be a 3. I'm just recopying it from here. This is another typo. That should be a 3, which is really weird because I really would have just copied and pasted that. This should be a 3. 5 over 5 will cancel, make a 1. Distributing the 1/3 through, you just get negative cosine t, negative sine t for your normal unit normal. The bivariate is the cross product of the unit tangent and the unit normal. Going through the cross product, you should get that, except that you should have, goodness, lots of typos on these slides. This should have a j, this should have a k, because this 4/5 sine of t came from this determinant, and this negative 4/5 cosine of t came from this determinant. So there should be a j attached to the end of that, and a k attached to the end of that. So now when we plug in pi into this function, we notice that we get the indicated point. So now evaluating the unit tangents, the unit normal, and the bivariate normal vector at that pi value, we can just plug those into the various functions and get those vectors. All right, we use the bivariate normal to give us what's referred to as the oscillating plane. It's the plane that that contains both the unit tangent and the unit normal vector. So it's the plane that just touches the graph of the space curve. The whole plane would be kind of tangent to the graph of this curve. So the bivariate normal will serve as a normal vector of that plane. So in this previous example, here's our point, and our bivariate normal was 304, 1/5 of that. So we can use that for our normal vector for our plane, and gives us, this is our equation of our plane. And we can see here's our space curve. Here's the plane that just touches it, and it contains the unit tangent and the unit normal. Here's the tangent, here's the normal. And here, this would be your bivariate normal, being normal to the blue plane. Zoomed in a little bit. The osculating circle is a circle that is tangent to a curve and is on the same side as the unit normal vector, and it has the same curvature. So let's find the circle, and we'll see a picture of it, and it'll make a little bit more sense of what I just said. So let's say we wanted to find the oscillating circle for this ellipse. The first thing we need to do, oh, there's a graph of it. So we want a circle that mimics this curvature. So we're going to have some very large circle, you can imagine, at the end, because it's going to mimic this curvature, which is pretty flat. So the first thing we want to do is notice that we can actually get our curvature formula, if we have a function of x, to be boiled down to this formula. The absolute value of the second derivative over 1 plus the first derivative squared raised to the 3/2 power. So in this case, if we solve for the top half of the ellipse for y, you can get your f of x, or y, is equal to the square root of 1 minus 1/9 x squared. We take the derivative, take the second derivative. We want the curvature at the point x equal to 0. Plugging in 0 into the first derivative, we get 0. Plugging 0 into the second derivative, we get -1/9. So that the curvature just becomes 1/9 using that formula from the previous slide. The radius must be 9. We also notice that, if I go back to the curve, let me go back to the previous slide, the tangent vector at this point 0, 1 would be horizontal. So the unit normal is going to point downward. It's going to be in the direction in which the graph is curved. It's going to point this way. So when we want to find the center of the oscillating circle, well, it has to be going towards the unit normal vector. So it's going to be 9 units. This is going to be the radius of your oscillating circle. It'll be 9 units below the point 0, 1, or at the point 0, -8. So the center is 0, -8. The radius is 9. So the equation of the circle would be x squared plus y plus 8 quantity squared equals 81. And here's a graph of that oscillating circle with the graph. And as we mentioned, we envisioned that that graph of that circle was going to be big because that function, or I should say that ellipse, was pretty flat at the point 0, 1.